Yeah, thanks a lot, Kai, for the kind introduction. Christian, thanks a lot for this beautiful talk, providing the motivation for my talk now, namely high-precision measurements for nuclear and neutrino physics studies. And I would like to start with a broad overview on the motivation and fields of applications. We'll continue with the basics of PENTATRAP mass spectrometry. That's what we are mostly doing, namely a high-precision measurement of the Q value of the mass difference of the mother and the daughter nuclides. And we'll then move on to recent results and future perspectives. To start with a broad introduction, atomic and nuclear spectroscopy probes fundamental physics, and I give a few examples, but we'll cover only some of them here in the context of this talk. One great application of atomic nuclear spectroscopy is, among others, the detection of the variation of constants in case it exists. So the example given here would be a difference, an energy difference between ground and excited state, and if that varies, one can detect a variation of the fine structure constant alpha. Other possibilities are, of course, neutrino masses. So atomic nuclear spectroscopy allows to provide information on neutrino masses like the Q value. I will come to that later. We can also probe parity violation, EDM, fifth force search. That's what I cover a little bit at the very end of my presentation, and also test of quantum electrodynamics. That's what we can do with the techniques which I'm going to introduce. The probes which we are using are either radionuclides, and one example is given here, namely the isomeric state of thorium-229, which is now proposed as a nuclear clock which exceeds the present precision of atomic clocks by at least an order to 2 orders of magnitude. We are going to use antimatter to probe fundamental symmetries like charge-parity time reversal symmetries, and we are using highly charged ions, among others, to perform fifth force searches. The quantity of interest is the mass of an atom or the mass of a nucleus. In fact, when I'm going to talk about nuclear masses, what we are interested in is the nuclear binding energy. And the reason for that is this equation here. So the atomic mass is given by n times the neutron mass, z times the proton mass, z times the electron mass minus the binding energy. And the binding energy is, of course, equivalent to the mass. And depending on the precision you can reach, you either probe the nuclear binding energy, which is typically in the order of a few MeV per nucleon. So you need relative mass uncertainties in the order of 10 to the minus 6 to 10 to the minus 8 to probe that. But if you would like to probe atomic binding energies, which are in the order of a few electron volts, you need at least relative mass uncertainties of 10 to the minus 10 and better. And that's exactly what is needed, for example, for the application that Christian mentioned, namely the Q value in the tritium decay. So 70 milli-electron volt out of 3 GeV is in the order of 2 times 10 to the minus 11. And we would like to improve that even further by a factor of 3 to 4. The technique of choice is a PENTATRAP mass spectrometry technique. It's given here, so you have simply a superposition of a strong magnetic field and a weak electrostatic potential. So the strong magnetic field forces the ion with a charge to mass ratio Q over m on a circular orbit. It reveals a very characteristic oscillation, and we have to measure the number of turns the particle does in a certain time. Of course, the ion can escape along the magnetic field lines. It's only comprised here in 2D, so we have to add an electrostatic potential as it is given here, and now you have the ion stored in 3D. To give you a feeling, the magnetic field is typically 7 Tesla in our case. The electrostatic potential is typically 10 volts. That's how the superposition of the ion motion looks like. It's a composition of 3 independent eigenmotions, an axial oscillation, a magnetron oscillation, and a modified cyclotron oscillation. That's how our PENTATRAP looks like, with an hyperbolical shaped ring electrode, end cap electrodes, and some correction electrodes to adjust the field as perfect as possible. This is how it looks then in reality. This is our most modern precision PENTATRAP. In fact, it's a stack of 5 PENTATRAPs on top of each other, and we'll come back later to that. It is machined with a precision of better than 1 micron. So every piece of this trap is machined to better than 1 micron, put together in a clean room. In fact, the clean room of Manfred Lindner, who is here also in the audience. We were allowed to use that, which was really amazing in order to get it as clean as possible. And that's how the overall setup looks like, with the superconducting magnet, the cryostats, and quite a bunch of electronics. What you should take home, the quantity of interest, is the cyclotron frequency. It's the number of turns the particle does per second. It's given by the charge to mass ratio times the magnetic field. So our experiments are as easy as it is given here. So by knowing the charge state and knowing the magnetic field strength from the cyclotron frequency, you can deduce the mass of the ion. It's not quite that easy, because you have to know, if you would like to measure the mass down to 10 to the minus 11, you also have to know the magnetic field down to 10 to the minus 11. So we have to do our in situ magnetic field calibration. I come back later to that. And you might have seen here that nu c is not given in this plot. You see 3 frequencies, but not nu c, but there is a relation to that, which is called the invariance theorem. So this equation even holds in case that there are non-perfect field adjustments. So the sum of the square of the 3 individual frequencies gives you the true cyclotron frequency. And our detection method is non-destructive, so we measure the induced image current of the charged particle in the electrodes. Let me come to a number of results, and since it's a partly nuclear physics conference, I would like to start with a nuclear mass measurement, which is the most prominent or the most easiest one. It's the nucleus of the hydrogen atom. So it's the proton mass measurement, which is in fact a fundamental constant that enters many other fundamental constants, like the Rydberg constant. So we were interested in the building blocks of matter, and you see here the hydrogen atom with the proton as the nucleus and the electron in the shell. And what we did is we compared the proton with 12 carbon 6 plus. So it's a highly charged ion. It's the carbon where you have removed all electrons to come as close in Q over M as possible. The reason why we use 12 carbon is that the unified atomic mass unit is defined as 1/12 of the mass of carbon 12. So this is our reference for the calibration of the magnetic field, which is almost uncertainty-free. The uncertainty that comes in is the uncertainty of the binding energy of the 6 missing electrons. So you compare the cyclotron frequencies of these 2 species. You do that for a couple of weeks, and then you end up with the world best measurement of the proton mass, improved by a factor of 3. And this is the latest value tabulated in CODATA, the compilation of all fundamental constants with a relative uncertainty of 3 times 10 to the minus 11, just published 1.5 years ago. However, we discovered a discrepancy to all previous proton mass measurements by more than 4 standard deviations, and I come back to that later, how that is now resolved, because that was also of importance for the helium Q value measurement. To give you a kind of an overview, my student who has done the experiment, Fabian Heise, is also very much interested in some science history. So he digged into the literature, and he found around 220 proton mass measurements over the last 200 years. It even goes back, and you see here the relative mass precision of the proton mass as a function of the year of publication. The first publication is from the 1820. At that time, gravimetric stoichiometry, don't ask what it is, was used to measure the proton mass at the level of 10 to the minus 2. Later on, single and double focusing spectrometers came into the game, and then mass synchrometers, where for the first time a revolution frequency was measured. And then the latest development in the last 20 to 30 years, PENTATRAP mass spectrometry, after the Nobel Prize was given in 1989 to Demold for that technique. And that's our latest value at the level of 3 times 10 to the minus 11. We are now just now preparing an experiment where we might boost that by another factor of 5 to 10, mostly by reducing the temperature of the single proton in the PENTATRAP. Of course, when you have measured the proton, we came up with the idea why not to measure also the mass of the antiproton, because that would provide a stringent CPT test. We did that, but we didn't compare it to 12 carbon 6 plus. Rather, we compared the proton with the antiproton. In fact, to be fair, we compared the H minus ion with the antiproton. You might think about why we use the H minus ion and not the proton. It's not so, it's not so difficult. Remarkable for that experiment is that the temperature of the experiment is minus 270 degrees centigrade. The pressure which we have reached is at least better than 4 times 10 to the minus 19 millibar. I think that's the best pressure ever measured in the world. It's not a direct measurement, it's an indirect measurement, because our antiproton was stored for several years. So a single antiproton stored for several years. And from the annihilation cross-section, you can calculate back what the vacuum is, so it must be better than 4 times 10 to the minus 19 millibar. We measured the cyclotron frequency ratios of the proton to the antiproton, well, the H minus ion, so it's the proton with 2 additional electrons to the antiproton. And this is the frequency ratio. And if you do right, and we did a blind data analysis, we ended up with the value Q over M for the proton, antiproton to the proton of minus 1 point, and then comes 11 zeros and the 1 with a 69 uncertainty in the last digit. That's the most stringent test of CPT symmetry in the baryonic sector at the level of 7 times 10 to the minus 11. Of course, it's not that easy. And the reason why it's not that easy is that we use the H- ion. So we have to correct the two additional electrons, the masses of two additional electrons. You have to correct for the binding energy for the first electron, the electron affinity of the second electron. And unfortunately, the two electrons, they like to move in a kind of correlated motion, which is called polarizability. So you even have to correct in a blind analysis for the polarizability. And finally, you end up with this value, and that's the result which we released. Okay, so after we have measured the proton and the antiproton, we of course also wanted to measure the electron. We did that in a very similar experiment and even improved the electron mass by a factor of 13, and these are the latest two measurements on the mass of the electron and the proton. So now already two constitutes of matter are measured with a world record, and what is missing is the neutron mass. How can we get access to the neutron mass? Because neutron is neutral, so you can't store it as a charged particle. Well, we used a trick, namely we measured the deuterium mass. The deuterium mass has in the nucleus a proton and a neutron, the electron and the shell. And since the binding energy of the proton and the neutron is known, you can extract from the deuterium mass the neutron mass. And that's our latest value, just submitted to Nature. I'm not allowed to give the last two digits, but even the deuterium mass is now improved by a factor of 2 to 3, but you have to use nuclear spectroscopy for the binding energy. What is the link to this conference here? Well, the link is that we would like to go next to the tritium mass, which is the next heaviest system after we have measured hydrogen, deuterium. Obviously, we would like to do tritium. The motivation has been given by Christian, where the latest result of Katrin is better than 1.1 electron volt over c squared on the upper mass limit of the anti-electron neutrino mass. And here comes a problem Christian did not address, but I would like to do so, which is called the puzzle of light atomic masses. So Van Dyck has measured something like 15 years ago the deuterium mass versus 12 carbon. We have measured the proton mass versus 12 carbon. 12 carbon is the mass standard. At Myers, that's the value Christian reported on, has measured the Q value of tritium and helium-3 by measuring these two atomic masses versus the HD molecule. So it's the hydrogen-deuterium molecule, where you might debate on how accurate this measurement is, because the HD molecule has excited rotational vibrational states, which are long-lived, in the order of a few hundred millielectron volts. So you have to guarantee, if you use that as a reference, that it stays in the same state when you do the helium and the tritium measurement. Van Dyck has also measured the link between 3 helium and 12 carbon, so this gives now a link, which is nice because you can also take, and that's what we did, for example, you can take the binding energy of hydrogen and deuterium to get a link to the HD molecule. And now we have a closed circle. Now you can compare the masses which are given here to the masses which are given here via these two links, and you end up in the 5 sigma discrepancy. That was a real big puzzle, because that could indicate, for example, that the Q value Christian was reported on might be wrong by 5 sigmas, or one of the measurements here might be wrong. For example, the link between these two. So most recently, we have measured deuterium against 12 carbon. Ed Myers has measured deuterium against the proton mass, and that already reduced the discrepancy towards 2.4 standard deviation. So much, much better improvement, mostly because there's a 5 sigma deviation in the deuterium mass, which we have observed. And as said, we just submitted it for publication. Still, there's a 3 sigma discrepancy, and one reason for that might be that this link is wrong. So right now we are running an experiment where we would like to improve the measurement of 3 helium towards 12 carbon, and at the same time tritium against 12 carbon at the level of about 20 millielectron volts, which is 7 times 10 to the minus 12. And I'm pretty sure that by that we will resolve the discrepancy, which is still here in the order of 2 to 3 sigma. Going towards heavier systems, so that's one contribution to the light neutrino physics case. Christian already mentioned the Holmium project. I will be brief here because the next speaker, Christian Enz, report on that in much greater detail. But what also is required for that experiment for systematic checks is the Q value again. And the Q value as being the mass difference between the mother and the daughter state. In that case, 163 holmium, which decays to the excited state of 163 dysprosium. and that de-excites, and what needs to be measured is the total energy release, which gets done by metallic magnetic calorimetry, and Christian is going to report on that. What is required is the Q value, and we have done so, which is here exactly close to the endpoint indicated here. There have been in literature a number of measurements on that Q value, but there were also a big discrepancy. These had been the latest 2 microcalorimeter measurements, which are off by up to 8 sigmas compared to the accepted atomic mass evaluation value in the year 2014 at about 2.5 keV. We performed the first direct measurement of the Q value, the mass difference of holmium to tritium. Sergei Alexeyev did that work, and we ended up in this value here with an uncertainty of 30 electron volts, clearly indicating that the metallic magnetic calorimetry measurements are right. Christian Enz and his group continued afterwards to remeasure that by metallic magnetic calorimetry, and that's their value in a perfect agreement, the latest 2 values, with an uncertainty in the order of 20 to 30 electron volts. We are going to improve that, running right now an experiment where we would like to go down to 2 to 3 electron volts, again being in the ballpark of about 10 to the minus 11 for the next generation of the electron capture on holmium experiment. The technique to do so, it's very difficult to reach the 10 to the minus 11 level in the heavy mass region. So you have a nucleus that has a weight of 150 GeV, and you would like to measure that down to 1.5 electron volts. What we aim to do, though, is, this is again the cyclotron frequency equation, we would like to use highly charged ions. So we remove as many electrons as possible, because by that you boost the Q value here. So you increase the cyclotron frequency while the measurement precision stays constant. So by that you gain an order of magnitude in precision. That's the trick which we are going to use, of course, with the disadvantage that you have to correct for all the binding energies of the missing electrons. The apparatus that's able to do so is called PENTATRAP. Penta because there are a stack of 5 penning traps on top of each other, which I would like to explain now. Again, the magnetic field is unknown, so you have to calibrate that. And the calibration we are doing is by using a second ion. And this is now the technique indicated here. So these are the 5 penning traps on top of each other, 1, 2, 3, 4, 5. This stack is about 10 centimeters, so each of them is 2 centimeters. This is our measurement trap. This is one ion species, and this is the other one. So one is the reference of the other one. This is the measurement trap, so we measure the frequency here, we move that up, we measure that one here. If the magnetic field stays constant during that time, the magnetic field cancels out, and you get the cyclotron frequency ratio. Of course, we all know that the magnetic field doesn't stay constant. There are fluctuations by temperature, by time, and so on. So the idea is that we do that over time, and then we perform a polynomial fit of lowest order to the magnetic field, and then the ratio of these 2 frequencies provide us the mass ratio. So the magnetic field cancels out here. The reason why we are using 5 traps is that we can do, to double the statistics, we can add 1 species again to the 3rd trap, and now we can measure in 2 traps in parallel. By that, even measuring at the same time, so now even the time drift can be canceled out. I can tell you one trap is complicated, 2 traps are more complicated, 3 is horrible, 5 is almost a disaster, but we succeeded to do so. Okay, still not in use is the 5th trap. The 5th trap, we have the idea to store a kind of a monitoring ion which performs as an in situ magnetic field calibration. At the moment, we are thinking about using polarized helium-3 as a magnetometer. And we have already demonstrated to do so by having then reached 10 to the minus 14 to 10 to the minus 15 measurement sensitivity on the magnetic field. So that would be a real breakthrough. The first case which we investigated was, again, towards neutrino physics, namely the beta decay of 187 rhenium, because there's been a beautiful magnetic metallic calorimeter measurement at the uncertainty level of about 2 to 3 electron volts. So we use that as a test case to look into that. And what we are going to use is highly charged rhenium osmium 29 plus. So we remove 29 electrons to boost the frequency by a factor of 29. Of course, as said, to get the Q value of the neutral species, you have to correct for the binding energy difference of all of these electrons. So we did an experiment. This is our 5 penning traps, rhenium, osmium, rhenium. We swapped them around, measuring the cyclotron frequency ratio, and from that we extracted the Q value. And then we figured out the problem. So in about 50% of the cases, we got a frequency ratio as the one given here, the top one. In other 50% of the cases, we figured out the lower one, exactly different by 202 electron volts. That puzzled us a lot. So we thought there might be systematic effects, jumps in stability of power supplies or so, but it was always perfectly 200 electron volt difference between one and the other value. So we thought, okay, let's check that by using the same species. So instead of using rhenium, osmium, rhenium, we used osmium, 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 and measure osmium against osmium. And obviously, the value was 1. Sure, should have the same mass. We did the same for rhenium against rhenium, and in 50% of the cases, we ended up with 1. In 50% of the cases, we ended up in a difference of 202 electron volts. Now we had the idea, this might be an excited electronic isomeric state, a long-lived one. That's exactly what came out. The ground state configuration, that's now atomic physics. Please allow me to elaborate a minute on that. Rhenium-29 plus has the electronic configuration of a 4d10 electron. So it's a closed d shell having 10 electrons in. But by the production of the highly charged ions, it can also happen that one electron ends up in the 4f1 state. That's a highly forbidden transition. It's an E5 transition with a half-life of more than 150 days. With an excitation energy of around 200 electron volts, predicted by theoreticians like Soldan Hamer and Moritz Haverkort from the University of Heidelberg in our institute. And this is the latest result. We just got it accepted in Nature. It's the rhenium excited state 29 plus. This is the experimental value 202.2 plus minus 1.7 electron volts. So it's a 7 times 10 to the minus 12 measurement. These are the two theory values. The same we did for osmium. Again, a perfect agreement. And now comes the real unique thing. If that could be used as a transition for an optical clock, you would improve the time standard by a factor of 5 orders of magnitude, because it's such a long-lived state. There's no other way to detect such states except by PENTATRAP mass spectrometry. And that's a discovery of such a long-lived isomeric state. On the other hand, it poses severe problems for the applications in neutrino physics, because we have to make sure that such state does not exist. So in the case of holmium, if we would measure such a low-lying state, we would be wrong in the Q value by 10 electron volts or so, which would be a disaster. So we have to find electronic configurations which do not allow for these excited states. I'm almost at the end. The last few minutes I would like to spend on nuclear masses for fifth force search. So the idea behind is that you measure the nuclear masses of an isotopic chain, like the calcium isotopic chain, the even isotopes, calcium 40, 42, 44, 46, 48, and you do laser spectroscopy and to measure two optical transitions against each other and plot them in a so-called King plot. The King plot assumes that if you plot these two optical transitions against each other, that it's linear. And in order to demonstrate that, we did a number of measurements, which are mass measurements, which are all required at the level of 10 to the minus 11. And we did so as an example for the xenon case. So these are the stable xenon isotopes, 126, 128, 29, 30, 31, 31, 32, 134. This is the abundance of these isotopes, and we measured the nuclear masses of all of them at the level of around 6 to 8 times 10 to the minus 12. And the improvement factor is given here. The improvement factor for the most abundant species is around a factor of 4 to 7. They have already been measured at the level of 5 times 10 to the minus 11 in the past by Ed Myers and his group. But the least abundant ones, because our method is extremely sensitive, extremely efficient because of this multi-trap configuration, we improved even by a factor of 1,700, so three orders of magnitude. How can that be used for fifth force search? Well, by doing isotope shift spectroscopy. So you measure the transition energy by laser spectroscopy of one transition and compare it to the other transition, and the relation should be linear for the different isotopes. That has been predicted by Berengut just 1.5 years ago. The isotopic shift is a function of the field shift, which depends on the size of the nucleus. So what you need is the nuclear charge radius. And it depends on the mass shift, because isotopes become heavier and heavier if you add 2 and 2 and 2 neutrons. So that's the reason why the nuclear masses need to be known so accurately. As said, if you plot 2 transitions against each other, you get such kind of a linear behavior, and this is the example taken from the calcium chain, and you see an amazing linearity. And now comes, a fifth force would exist and would couple by a dark matter particle to the neutrons, you might see slight deviations from this linear trend, like it is indicated here. This would give this additional coupling term here. I know, as soon as we would see a deviation, we would first hint towards a nuclear physics effect, like, for example, a deformation in the nucleus. That could be exactly the same. You could have other problems, but as long as you don't see a deviation, you can still claim that you have set an upper limit on the fifth force. That's the motivation behind that, and it requires all the involved nuclides to be measured to better than 10 to the minus 11. That's exactly what we have demonstrated for the xenon case. So that's really a very exciting new perspectives for nuclear physics research, because it requires highest atomic and nuclear spectroscopy measurements. With that, I'm at the end. I hope I could convince you that PENTATRAP mass spectrometry has reached an amazing precision, even on exotic systems. It has opened up many new fields of research in neutrino and nuclear physics, things which we have never thought about that maybe 3 or 4 years ago, mostly because of the precision that has been reached. And with that, I'm at the end. Thanks a lot for the invitation and your attention.